Can hear me. I'm Arun, and I am a computer vision engineer at Redicell. So we are working on a product called Nemo, as in Finding Nemo. Basically, we're building a search engine for automotive data. We collect a bunch of different types of sensor data like camera, LiDAR, radars and stuff, and we build a query engine that extracts scenarios that we would like to, or that we would want to extract. So in today's talk, I will be focusing on a few challenges in training machine learning pipelines, specifically focusing on hyperparameter tuning and how we overcome them using Ray. So at the beginning, I'll talk about some of the basics and briefly walk you through internal pipeline that we have, and also at the end show a demo. Hopefully the demo works. So so what is hyperparameter tuning, right? So why do we need to do that? In the figure on your right, as you could see, some of the machine learning models that has been built over the past 72 years. The y-axis shows the number of petaflops used for training each one of those models. A petaflop is basically 10 to the power 15 floating point operations. So now, as you could see, the number of computation, the amount of computation required for training these models have been growing quite exponentially over the last 70 years. And we're dealing with hundreds of millions of petaflops of operations in the, for training pretty recent machine learning models. So to learn a robust AI model, we need to let these algorithms learn an optimal set of weights or parameters. Whereas hyperparameters are like, think of them as meta-parameters, which determines or controls how the learning of parameters is achieved. Like how fast can we learn? Where do we start? What are the initial weights? And where do we stop? How many iterations of data should you go through? So those are basically hyperparameters. This is for mostly non-technical folks. If you guys are technical folks, you probably already know these things. So coming to the challenges, what are the challenges? Here are some of the a simple graph where we're trying to achieve a higher accuracy, and each line represents an experiment. So basically, over the number of iterations, we achieve some higher accuracy based on the different types of initialization used. So in this case, one thing to notice is that each of the hyperparameter basically determines the outcome of the experiment, largely. So if I have to train a machine learning model that takes hundreds of millions of petaflops, I'm dealing with a grid search of these hyperparameter, and each one of those experiments is going to consume such extensive amount of memory and compute costs. That means if I'm dealing with like half a dozen hyperparameters, the grid search through that would mean that I'd be dealing with hundreds of or thousands of experiments. So that's basically thousands of times of training these models. Each one itself is each individual trial itself is expensive. Sometimes it can go up to 3 to 5 days and cost thousands or millions of dollars sometimes. And this scale is really quite exorbitant. So how do we optimize this is the question. And I see the slide missing. Okay. So the focus is on trial distribution. The goal is to minimize the number of trials that we spin off for tuning hyperparameters, and also achieve some early stopping techniques where we don't have to train each of the trial to the end to figure out that this didn't work. We could figure out that this didn't work as early as we could and then stop them. That way those resources can be used or allocated for other trials that are actually performing well. So that is basically the overview of the trial distribution. And before jumping into the parameter tuning, we'll go through some of the basics. Logging, basically RayTune has a extensive support for other logging libraries like TensorBoard and then MLflow, Weights and Biases, some of the commonly used loggers. And the need for logging libraries is pretty extensive because, as I mentioned, these experiments, individual trials could be quite expensive. And if we lose track of experiments, or we confuse one experiment for the other, or we repeat experiments, basically that's going to be even more costlier. So proper logging is kind of like quite critical for these hyperparameter search tasks. And yeah, as I mentioned, poor logging often leads to pretty exorbitant amount of money spent on doing hyperparameter tuning. And finally, parameter search. Ray again has this. RayTune provides or allows integration with some of the most commonly used parameter search libraries like HyperOpt, Nevergrad, and Optuna, etc. So these parameter search libraries basically does optimize the grid search process. So as I mentioned, we have a few hyperparameters, maybe half a dozen hyperparameters that we want to search across, and there is a range for each hyperparameters. Those parameters could be learning rate, where we have a continuous range, or could be a type of optimizer, which is more of a categorical. So these parameter search libraries allow us to do efficient search. I'll talk about those in detail in the next few slides. So the core of these parameter search libraries are schedulers. So in this case, the most commonly used two types of schedulers are asynchronous hyperband schedulers and median stopping rule. So asynchronous hyperband scheduler, I don't want to jump too much in detail into technicalities of that, but basically it's a hyperband optimization algorithm that performs a technique called successive halving. So think about it this way: if we start with 100 initial trials to search half a dozen hyperparameters, and then within a specified number of iterations, we're going to cut that by half. Like say, for example, only 50 of them goes through. And then another, within the, repetitively, we just get 25, and then 12 of them, and then 6 of them. So ultimately, we get that one best performing model that actually has optimal hyperparameters. So that's basically the asynchronous hyperband scheduler. And median stopping rule does a similar algorithm, does work similarly, but basically it identifies what is a median performing trial in terms of some metric like accuracy, and it stops everything below that. So basically, it's in a way successive halving, but does it in a slightly different way. And Ray supports a bunch of development frameworks like TensorFlow, PyTorch, XGBoost, Keras, and everything. So it's pretty easy to integrate. Seamless. Irrespective of whatever the libraries that you're using, it's basically Ray's minimally invasive and easy to integrate into existing architectures. So we found that true as well in our use case. And so I'll talk briefly about an internal use case that we have. And in our product, we have this bunch of neural networks. So we basically deal with drive data. Think about a dash cam or a set of rear view camera mirrors. Cameras placed on rear view mirrors that are facing frontward. So the goal is to extract interesting scenarios, like say, for example, a pedestrian crossing into the road, or some car overtaking the ego vehicle. Such interesting scenarios might be occurring while the drive data is being collected, but it is hard to query such instances. So that's where we come in. That's basically the product that we are developing. So we have lane detection algorithm that basically identifies lane pixels and classify them as like, okay, hey, this is a continuous white, a white lane or yellow lane or dotted lanes and so on. And also we have object detection algorithms, which basically sometimes 3D object detection algorithms, sometimes 2D detection combined with depth prediction. We identify the 3D position, model interactions and stuff. Tracking algorithms, so bunch of neural networks, and we have to do hyperparameter tuning for each of them for the algorithm to perform efficiently at the inference time. Here's the architecture. Basically, a bunch of perception networks that extract some semantic information that involves modeling the actors and identifying them as a scenario. That way, at query time, we can search, say, hey, for example, give me all the instances of an accident that involves a pedestrian, or give me all instances of a cut-in that involves an SUV, something like that. And that is basically the runtime, inference time application. So how we use Ray, basically, as I mentioned, Ray is quite minimally invasive and fairly simple to integrate into existing library. So the core of this RayTune algorithm is to call a method called tune.run, where we have a bunch of parameters, starting with your training function that basically is a Python function that calls your training model, and then your metric, what you want to log. Say, for example, I want to achieve higher accuracy. That's basically a metric, and then like what is the type of thing you want to minimize the loss or maximize the accuracy, something like that. That basically is a mode, and then some configuration, the parameters, like okay, what are the parameters I want to search? Learning rate or initial learning rate, momentum, weights, and etc. And a scheduler. So as I mentioned, like we have been playing around with a couple of schedulers. One is hyperband scheduler, and the other one is like a median stopping rule. But in this experiment, we have been, in this demo, we will be focusing on the hyperband scheduler. And also, wherever you define the training function, which was the first parameter of your tune.run, you call this tune.report. That's basically where you tell which metric, in this case the accuracy, which is a metric, we call them the variable to be maximized. So these are basically the minimal code you need to modify in your training pipeline to actually have RayTune set up there. And bunch of other things that you could do is resource handling. So I have a GPU cluster with like 96 GPUs and some 200 CPUs and so on. So how do I optimize this thing? How do I maximize the resource utilization? And how do I kind of like load balance it? Do I have to do manually, or like that's a major challenge, right? Because sometimes it's resource handling that takes most of the effort. So Ray takes care of most of these things efficiently. So basically, you can mention the number of CPU cores and GPU cores that you want. You can even mention fractional ones, like okay, if the GPU cores is like 0.5, it's going to basically use half of the cores. And if the CPU cores is fractional, basically it's going to cut the process into two and queue them. So it's basically fairly straightforward, actually. So yeah, this just by passing a variable called resource per trial allows us to handle it more efficiently and more elegantly. So now coming to tracking, where some of the major advantages that we see with Ray is it allows seamless integration with other other logging tools and other parameter search tools. So one of the logging tools that we use here is MLflow. So using MLflow is again relatively easy with Ray. You just have to basically get the tracking URI, which tells us where exactly are we logging this data, and call these three methods basically: log metrics, params, and artifacts. So metrics, what are the accuracy or validation loss or training loss, etc. These are metrics basically you want to track over time, that changes over every iteration. Parameters are something like initial learning rate. Okay, what was the initial learning rate used to start this trial? What was the initial momentum used to start this optimizer? How many epochs were it initialized it for? So these are some of the parameters that we could log, and artifacts are basically the trained models. So okay, the best trained models saved somewhere. So everything, think of them as like a single entry in a large interactive table. I'll show that in the demo as well, how MLflow works. So this allows efficient experiment tracking for these large-scale parameter search experiments. And Optuna, the parameter search tool that we use here. So again, integrating Optuna with the Ray pipeline is fairly straightforward. So basically, there is a method defined by run Optuna. So the defined by run allows us to search across categories. Like say, for example, which optimizer should be used? Is it like a gradient descent or Adam optimizer, or any of the types of optimizer are available? And also we can search across a range of inputs. So say, for example, what would be the initial learning rate? So we can mention a range. So in line 4, where we could suggest the range of each of the trial, for initial learning rate. And in line 7, we have the learning rate momentum, similarly suggested by using a range. And also, it's not just for continuous ranges. This would work for categories as well. In line 2, where we can actually give a bunch of optimizers, and it's going to search. Basically, it's going to do a grid search, not exhaustively, but more efficiently, and try to find the optimal set of what optimizer to use, what is the ideal starting learning rate, what would be the ideal momentum, and everything. I'll show them in the demo actually in a more, it'll be more clear during the demo. And yeah, that's basically what I actually mentioned, like, okay, how do we, the suggest float and suggest category operations, I mean, allows to search across categories or ranges and stuff. So finally, the demo where, James, could you switch it? So basically, yeah, it's a fairly straightforward MNIST training, MNIST classifier which we have for demo. We just need to run across a few import libraries and stuff, and then like this is our convolutional neural network, a very simple, quick to train one. We download the data sets here, and then basically this is our training pipeline where we log our metric here. So as I mentioned, log metric is one of the MLflow library, I mean like a function call among the 3 commonly used one: metric, log parameters, and log artifacts. So metric basically models a training loss. So in this case, this training loss varies across each. I mean, it keeps updating for with respect to each feed forward pass. So logging the metric basically is taken care of by the MLflow automatically. And this is our validation pipeline, and so this is where we actually have the whole MLflow pipeline combined with the network, where we initialize the network and then like call the MLflow run and then log all the data. So basically this is the logger and the trainer as well. So this basically is where we combine the parameter search library. We define the parameter search as I mentioned earlier in a couple of slides ago, where we identify, in this case search across 2 of the optimizers and a few ranges for initial learning rates, and in case of SGD, using momentum, have an initial range. Have a range for momentum as well. So finally, we combine all here. So MLflow for logger, and then Optuna for parameter search with the Ray library. So as I mentioned, the simplest way is to call tune.run, which has basically changed to tune.tuner in 2.0, which was released today. In this case, yeah, we pass we combined Optuna as well as MLflow, and then like call the tune.run. So I've already run it. It takes a while to actually get this thing, so I'm not going to run it again. So basically, if you could see, it searches across different optimizers and different iterations, and then different initial momentum, different initialization for momentum, and here different initialization for learning rates and stuff. And these are the accuracies obtained for each of these runs. So we could see that in the logger that we have here. So give me 1 minute. Okay. So while it loads, I can talk about a few other things. So yeah, one more problem that we had was that storing artifacts. So we are running a bunch of experiments here, like a bunch of trials where we don't know which artifact we are going to need. So if we are storing hundreds of checkpoints for each of the trial, if you're running like 200 epochs, we'll be dealing with thousands and thousands of models, which is going to log a lot of space. So hog a lot of space in the cloud. So what we did was we actually run all the search. We identify initial set of optimal parameters and just store them as a JSON file. And then finally we just pick the optimal hyperparameter combination and rerun the training with that to generate the efficient. high accuracy model basically. So that way we don't really save each of the artifact or model or checkpoint across all the iterations. We just save the combination and then we just log the experiment information and avoid saving the checkpoint and do that at the end. That way we save memory. And yeah, coming back to the MLflow experiments. So yeah, these are some of the experiments I just ran before the presentation, and then so MLflow is basically it allows us to compare these experiments like as we could see here. It's a bit slow. Sorry about that. So here are some of the run details, and then like what are the parameters used and what is the training loss achieved for each of them, and validation loss and F1 score achieved for each of the experiments. So it's kind of like organized by the experiment, and then the parameters used for the grid search, and also it provides an interactive graph. So this graph basically means that we can backtrack this from validation F1 score. So what achieved the highest validation is basically the Adam optimizer with a momentum initialized at 0.87 and a learning rate of 0.0045 probably. So we just initialized when we started the experiment, we just gave this bounds basically, so 0.001 to 0.006, and similarly we just gave a range for momentum and a couple of optimizers. So this basically is a grid search that it performed, and that gave us, okay, we have now the highest validation F1 score, and we can backtrack which are the parameters or which are the optimizers and exact values within the range that contributed to this one. So it's pretty interactive and easy to understand. And also, let me just show the. So here is how the optimizer is working. So basically you can see the successive halving or the hyperband optimization algorithm in work. So we initialized a bunch of experiments, and after a few iterations, some of those experiments have been stopped because they didn't do just as good as others. And so so these experiments are stopped basically, and then those resources were allocated back to the better performing experiments or trials, and they let continue, and at the end we just get that one most high performing experiment. So this is basically how the successive halving or the optimizer works. So it doesn't do an exhaustive grid search. It instead starts with the exhaustive grid search and tries to stop trials that are basically not going to give us good results. And yeah, that's mostly about the demo. And yeah, this is basically our setup where we use Ray with a bunch of other libraries that is supported by Ray, and train a neural network and achieve hyperparameter tuning for that. So yeah, questions? Go ahead. Sorry, go ahead.
Is mic on?
It's on.
So yeah, as far as the resource allocation, so with it, just to understand that scheduler algorithm correctly, so when you are killing off some experiments that aren't doing well, you just basically get more. Let's say you have GPUs or CPUs, you just allocate those to the distributed training on the other experiments, or can you actually use those to start up? Because I'm assuming you have a lot of these hyperparameter jobs running concurrently, so how do you manage that?
So yeah, I mean, in our case, what we found out was that it basically assigns new experiments. So it like, okay, if we have 200 experiments initialized and we have only 20 GPUs allocated, and each experiment takes 1 GPU. So it starts with the 20 experiments and basically stops experiments that are not performing well, and then assigns newer experiments. We haven't really seen how much of existing experiments resource being expanded and stuff, but it allows new experiments to be created and run, new trials to be begun. Yeah.
And then the other question is kind of just is there any way to sort of optimize this so that you can actually make it more efficient, not just across a single hyperparameter tuning search, but over you have multiple models that all are using the same resources, probably in Kubernetes or whatever you're running.
Sure. At this point, we are just to reiterate the question. So basically, he was asking, can we just your question is, can we just optimize it for in a way that multiple such experiments or like parameter searches can be happening at the same time, and can this setup be extended for that? Is that your question, right? Yeah, so that actually is, in a way, we are controlling that manually so far. So initially, when we have the resources, we're using, we're allocating, okay, hey, depth prediction takes a third of the resources, and then we kind of like upper bound it, I mean, like in a way. And so far, we haven't really tried around playing with automating that part, and I'm not sure whether Ray supports that, but at this point we are doing it one at a time. Like we initialize experiments and number of trials and then allocate some resources, and the resources are efficiently used within that particular bunch of experiments, but we haven't really tried across multiple network, optimizing multiple networks at the same time. So yeah, I hope that answers your question.
Yep.
Okay, thank you. You have a question?
My question is, do you have to reserve resources for other tasks rather than tune.run? Because I've used this before, but I see there are a lot of times that the trials will be pending like all the time. So I'm not sure if this is a resource leaking thing or it's just you have to set some buffers for other tasks when you integrate with other packages like MLflow.
So at this point, we kind of like, okay, when we run an experiment, say for example, we have a segmentation network and we are trying to run a parameter search for that, we kind of set the upper bound on available resources for now, and then we run just the parameters, I mean like search experiments, and then within that we often it automatically queues. We often have a much larger number of trials that we want to run, but lesser resource. In a way, okay, 20 GPUs available, whereas 200 experiments to be run. So it starts with 20, and then like, okay, keeps stopping experiments and respawning new ones. And basically at the end, it identifies some of the best performing experiments. So we haven't really worked on queuing anything manually, or we haven't really focused on I hope that answers your question, or like.
For this example, how large is this like array cluster for this notebook environment?
How large is what?
Like how much CPUs and GPUs for this array cluster?
So in this case, we just have one CPU and one GPU, just for demo actually. Yeah.
Okay.
So if you are running 200 experiments, so basically one CPU and one GPU are utilized in full. If you use half a GPU and one CPU, so one experiment is hogging the GPU, and then not only half of the GPU is being utilized. So it's kind of like, yeah, we initialize it in a way that, okay, we can assign them for 20 GPUs and 20 CPUs, where each experiment can take one CPU and one GPU core and run. And then if you have 200 experiments, after the first few experiments are stopped, automatically Ray passes on the next set of experiments that keeps running basically. So yeah.
I see, got it. Thanks.
Your question?
Where?
I think, okay, there are two questions here.
You first. Okay. Who was it?
Sorry about that. 1 minute, yeah.
It's going to be a quick one. How do you set the ranges that you search over for algorithms and different optimizers?
So yeah, it is basically in a way hyperparameter, I would say. We just start, because we initially, okay, in our case, we play around with a few experiments before running the parameter search. So we have some range in mind, at least to start with. Okay, we have some baseline. Now the range could be around the baseline is what we assume. And then, okay, if the learning rate is 0.0005, now we can actually start from 001 to 0.001 or something like that. So that's how we actually initialize the learning rate. It is more of like at this point intuitive. We don't really know. There is a bunch of limitation to how much we could search, right? Because it could be we want to limit the number of experiments or trials as well. So yeah, that's how we initialize it. So we initialize it around the baseline that we estimated before the experiment. Actually, that answers your question. Thank you.
And then one last question. Who had their hand?
Okay, he has a question. Yeah. I will come back to you. Yeah.
Yeah. So how does your actual training, which you do in the company, look different from like just running a Python notebook? And in terms of like the output of one workflow goes to another, and how do sharing of resources happen? Is there any?
Sure. In our case, as I mentioned, we have basically lane detection and object detection networks. So though at inference time we have a workflow where one network's output is fed to the other, and and so on in a more sequential manner. At training time, each network has defined loss and accuracy metrics that we need to achieve. So at training time, we do not really kind of leverage or use the dependence. At training time, basically we have said, okay, say for example, if it is a lane detection algorithm, which would be used for object tracking or like object model interaction modeling. But at training time, we have, hey, this is a lane, here's a segmentation, here's a classification, and we have to achieve F1 score of this, and training and validation accuracy of this and stuff. So that's basically our requirement. So at training time for hyperparameter tuning or like the parameter search, we do not really focus on, or we do not need to focus on the sequence or how this network works with the other or within the pipeline. It's kind of like a set, we have a set of requirements that we need to achieve for this particular network, and then we just try to achieve that. At inference time, basically we just wrap things around. So once each network is efficiently working or like optimized well, then we assume that the whole inference pipeline is optimized. That's how we work at this point, yeah.
Yeah, these are great questions.
Okay.
We have lunch now, so if you have further questions, feel free to come talk to Arun.
Sure.
Thank you all for attending.
Thank you all.